Alright, here we are studying Chapter 5, Work and Energy. So you start off with, what is work? And physics would say that work is a product of a force that's applied to an object over a certain displacement. Which means, if you have a force and a displacement, if your object does not move, you did no work to it in the scientific sense. Now you're accustomed to perhaps saying that work is a task or a job or something you have to do. Well, so for the example, Bob worked on his homework. That's the everyday sense of the word, the task. Bob worked on his behavior. Again, it's an everyday task. Bob did work in his car this week and changed the oil. Well, we're talking about doing a job here, not applying a force over a given distance. Bob did work on his car this week and he pushed it into the gas station. Well, there we're talking about applying a force for a distance. That's the scientific use of the word. And then Bob did work on his pencil when he wrote his name. Again, we're talking about applying a force for a distance while writing a name. Calculating work. Work equals force times distance. And then you have an angle involved. So in our sample problem here, we have 50 newtons of force times 3 meters. And then you have the cosine of 30 degrees. Okay. Work equals that. So if you use your calculator and you calculate this out, well, obviously the 50 times 30 is 150. And our unit here is the joule. 150 joules. Well, if you then, 50 times 3 is 150. If you then multiply by the cosine of 30, the answer drops. It drops down to 130 joules. So in reality, in our sample, where we're pulling the vacuum backwards with 50 newtons of force for 3 meters at an angle of 30 degrees, we get 130 joules of work out of that. Now the reason this drops with the angle is, think about this. If you put in your calculator the cosine of 0 degrees, meaning pulling straight back, you would get a factor of 1. You'd be taking your work times 1. And if you put in your calculator 90 degrees, well, in that case, you put the cosine of 90 and you get 0. So think of this. If you're lifting up, are you doing any horizontal work? Well, no, you'd be lifting upwards. Another example. Your car runs out of gas and you have to push it into the gas station. If you really want to get the most work out of pushing your car into the gas station, you should push straight sideways on the tailgate or the trunk of it. But if you were to push down on the trunk, you're not going to move your car. You're doing no work. That's what our angle does to us when we're calculating here. It adjusts the amount of work we do because of having our forces at an angle compared to the motion of the object. So an example here, if we lift a bowling ball up 1.5 meters for 6 kilograms. Well, let's see here. Work equals force times distance, right? Work equals force times distance. So we would say that our force, we don't have force in the problem. Let's see, work equals, we don't have a force. We don't have a force in the problem. We have to fight the force of gravity, though, to lift our bowling ball. And if we lift our bowling ball with a nice constant velocity, that means that the force down and the force up are equal to each other. So we can say the force of gravity here. So we can say 6 kilograms times 9.81 meters per square second. And then we'd have to multiply that by our distance times 1.5 meters. And when you multiply that out, your work ends up equaling, hit the calculator there, 88.29. 88.3 joules is our amount of work we do lifting our bowling ball that far. Coincidentally, we'll learn later on that we're storing potential energy in the bowling ball, and the amount of potential energy stored in the bowling ball is the same as the amount of work done moving it. But that's for another section. Well, what if we take that bowling ball right here, our bowling ball, we had it at 1.5 meters, we lift it up over our heads and bring it right back down. And we want to know, how much work did we do here? Well, if work equals force times distance, well, in this case, our distance is 0. we have no displacement. So 0 meters, therefore we get 0 joules of work. Whoops. 0 joules of work because we had 0 displacement. So an example I use of this in class is when I was a kid, we did some landscaping and we had to move this gigantic rock. And we had to have 2 tractors for it even. We lifted the rock up, moved it across the yard, and put it down. And then the lady says, I liked it back where it was. So we again used the 2 tractors, picked it up, and put it all the way back across the yard, back where it was originally. Now we labored on that rock all day, picking it up, securing it, moving it, setting it down, putting it down all nice. But in the end of the day, we went over and we came right back and put it in the same spot. The displacement of our rock was 0. Therefore, the net work done on that big rock was indeed 0. Another thing about work is a scalar function. So if you have the direction of the force and the direction of the displacement here, if you push forward and it goes forward, guess what? You did positive work. If you push backwards and it goes backwards, you did positive work. But what if it moves backwards while the force in question is forward? Well, if you want to give these signs, maybe positive times positive gives you a positive, and negative times negative gives you a positive. But here you'd have a positive and a negative. It's going to come out negative. And here, the direction is forward, but the force was backwards. Again, you end up with a negative. Well, for this to be true, you're probably talking about a resistance force. For example, if you're pushing a desk to the left, friction is to the right. Or go vertical with this, as you fall downwards, air resistance pushes upwards. These are resistance forces, and resistance forces do negative work. So what does Bob have to do to this rock to do work on the rock? Well, you'd say, well, Bob has to move the rock, and boom, there's the homework that you're responsible for associated with this homework problem, or with this assignment.